Lecture 27, Inductor De-energization Equations. The objective of this lecture is to understand how inductor de-energizes through a resistor when the source is removed. We will also be finding out how voltage and current varies with time and how the inductor de-energizes. So the circuit consists of a resistor R, an inductor L, a switch S which is closed at t is equal to 0, and the initial current will be I naught. So let's talk about initial conditions first. At time t is equal to 0, the switch is turned on. Therefore, the inductor is behaving like a source and the current will come out of the positive terminal and the current value will be simply equal to I naught. Therefore, the initial voltage will be equal to I naught R. And let's move on to steady state. At steady state, when this switch is turned on for a very long time, the current has died down to 0. Therefore, voltage also becomes equal to 0. Between initial and final condition is the transient state which we are concerned with. So let's try to derive the equation of I for this transient state. So in this circuit, on application of KVL in anti-clockwise direction, that is minus to plus, that is plus voltage across inductor, that is VL, and plus to minus, that is minus voltage across resistor, that is VR, is equal to 0. This equation is written like this. The value of VR can be obtained using Ohm's law since current I is flowing through it and resistance is R, so V equal to IR. So VL minus IR is equal to 0. Now inductor voltage is expressed in terms of current. So for an inductor, VL will be equal to minus LdI by dt, and minus comes as we have reversed the passive sign convention. So what is passive sign convention? Case 1, if the current enters the positive terminal, suppose it is like anything like this, then the voltage is taken as plus LdI by dt, and if we reverse this convention, that is current leaves the positive terminal, then we have to add a negative sign, that is VL is equal to minus LdI by dt. Now putting the value of VL in this equation, we get minus LdI by dt minus IR is equal to 0. We rearranging it, we get di by I is equal to minus R by LT. In order to find out di, we need to integrate both sides. So on integration, we get di by I, that is integration of di by I is log I, minus R by L comes out, and integration of dt is simply t plus a constant k. This constant k is obtained by using initial condition. So initially at t is equal to 0, I is equal to I naught. Therefore, the equation 1 becomes log of I naught is equal to minus 0 plus k. So from here, k is equal to log of I naught. So putting this value in equation 1, we get log of I is equal to minus R by LT plus log of I naught. And bringing this value to left side, we get log I minus I naught is equal to minus R by LT. So we will use the relation, that is log of A minus log of B is equal to log of A by B. And using this, we will get log of I by I naught is equal to minus R by LT. Now log is removed by introduction of exponential. So I by I naught becomes equal to e raised to power minus RT by L. So from here, I is simply equal to I naught e raised to power minus RT by L. And since I is function of time, it can be written in this form, as that is IT is equal to I naught e raised to power minus RT by L. For determining VL, we need to just replace the value of current I with this equation and solve it. And on solving, we get VLT is equal to simply I naught R e raised to minus RT by L. So I is equal to I naught e raised to minus RT by L, and VL is simply equal to I naught R e raised to minus RT by L. Now let's plot these curves. When IT is plotted with respect of time, we already knew that IT is equal to I naught e raised to minus RT by L. So at time t is equal to 0, IT simply becomes equal to I naught, that is this. And at time t is equal to infinite, IT is simply equal to I naught e raised to minus infinity, that is equal to 0. Similarly, voltage at initial value is equal to I naught R, and at time t is equal to infinite, VLT will become equal to 0. So if we put time is equal to L by R and solve this equation, we get IT is equal to I naught e raised to minus 1, E is 2.718. So from here, IT is equal to 0.368. That means that when time becomes equal to time constant, the current decreases to 36.8% of the maximum value. And similarly, the voltage at time t is equal to L by R also reduces to 36.8% of the maximum value, which was I naught R. These two plots can be clubbed into single plot like this for further understanding.